Hello everyone, I'm Hiromu. I'm glad to have a chance to talk to you. In recent years, heat sinks with high heat dissipation performance is required to support high power density. So today I'm talking about fin geometry to improve heat dissipation performance. Let me begin my presentation. Here is required heat sink performance. Electronic components in the power conversion circuit of PCs and EVs generated heat due to power loss. So heat sinks is installed to prevent malfunctions due to temperature rise. In recent years, acceleration of high power density by frequencies. So these high frequencies make circuits more miniaturization and increase heat density. So larger size of heat sinks is needed to get higher heat dissipation performance. But these larger heat sinks hinder higher power density in the package size. So we must need a heat sinks with high heat dissipation performance in a limited space. Here is the problems with major heat sinks. Flat plate heat sinks is used for major heat sinks. This shape is effective in gate contact area with refrigerant. But this shape has a problem. The problem that refrigerant makes a heat layer on the surface of fin. So heat layer causes that thermal resistance RFA become large. So RFA is that thermal resistance between fin and air. So problem is that refrigerant inhibits heat exchange by heat layer. So as a countermeasure, flat plate type heat sinks was cut a lot of small fins. So this shape is effective in broken gross heat layer. But this shape has a problem too. The problem is that heat is not transferred to top of the fin by small cross-sectional area. So this top area has bad heat exchange. So this problem is called lower fin efficiency. So lower fin efficiency is that the entire fin cannot use for cooling. But this shape has merit. The merit is low pressure loss due to easy refrigerant flow. I'm talking about cylindrical fins pin type heat sinks next. So this shape is effective in get good heat exchange by not form heat layer and high fin efficiency. But this shape has problem too. The problem is a higher pressure loss by generating vortex behind fin. So I talking about generating vortex, higher pressure loss by generating vortex problem. So this figure shows that static pressure versus and weight velocity characteristics. Blue line is a high pressure loss and red line is a low pressure loss. You know from this figure, the pressure loss determine active point of fan. So high pressure loss limited wind velocity, but low pressure loss get increased wind velocity. Here is the fin structure used on target. You know from previous slide, so flat plate heat sinks and cylindrical heat sinks have trade-off relationship, like this figure. Close to flat plate heat sinks, you get low pressure loss, but you get low heat exchange and low fin efficiency. Close to cylindrical fin, you get high heat exchange, but high heat pressures and high fin efficiency. So you know from this figure, the midpoint, if you use midpoint performance should be better. So I verify this method by using streamlined fins, because streamlined fins can change shape seamlessly. From this, aiming to improve heat dissipation performance by using the best of models. So actually, I made 3 different heat sinks model. First model is a streamlined fin 0.2 model. Next model is a streamlined fin 0.5 model. And last model is a cylindrical fin model. So these 2 streamlined fin model has a different cross-sectional area. So I verify 3 points. 1 point is a pressure loss, and 2 point is a heat exchange, and last point is a fin efficiency. From this, and I verify overall heat dissipation performance. Here is the experimental result of pressure loss. I measured with a differential pressure gauge before and after the heat sinks. So this graph shows that pressure loss and versus external wind velocity characteristics. Orange plot is a cylindrical fin and blue plot is a streamlined fin 0.5 model. Last green plot is a streamlined fin 0.2 model. You know from this graph, two streamlined fin can reduce pressure loss significantly. So you confirm in the simulation at wind speed of 1.0 meter per section vortex generating. So you know from this figure, two streamlined model can reduce vortex generating. From this streamlined fin 0.5 model lower pressure loss in the trade-off relationship. Here is the experimental result of heat exchange. I measured temperature and calculated thermal resistance from thermal equivalent like this. So you know from this figure, thermal resistance is can be separated to thermal resistance. So I measure and calculated RFA. So RFA can calculated by this formula. Next, I explain TF. So TF is a fin averaging temperature. So I measure TF at three different places because TF temperature of fin has different temperature depend on place. So this figure is thermal resistance RFA versus external wind speed characteristics. You know from this figure, streamlined fin shows the highest value of thermal resistance RFA. But streamlined fin 0.5 model and cylindrical fin model shows that similar thermal resistance RFA value. From this streamlined fin 0.5 model good heat exchange in the trade-off relationship. Here is heat exchange factors. So considering for heat exchange factors, this shows that thermal resistance RFA versus external wind velocity characteristics too. So you know from this figure, so here is a shear difference. So I consider heat exchange factor. So this figure shows that temperature cross-section in the simulation. You know from this figure, cylindrical fin and streamlined fin 0.5 model can spread more heat to the air compared to streamlined fin 0.2 model. So from these cylindrical fins and streamlined fin 0.5 model diffuse heat by vortex. From this heat exchange with air due to vortex must all be considered to improve heat dissipation performance in the trade-off relationship. Here is experimental result of fin efficiency. Fin efficiency must be considered in heat dissipation. So I calculate fin efficiency by using this formula. So Tv is a base plate temperature and Ta is air temperature, Tf is a fin temperature. So this figure shows that fin efficiency versus external wind velocity characteristics. So you know from this figure, streamlined fin shows that the lowest value of fin efficiency. So you confirm in the actual fin temperature distribution. Streamlined fin 0.0 model have a large difference between top and bottom temperature. That's why it caused lower fin efficiency. From this, streamlined fin heat sinks 0.5 model has a similar fin efficiency compared to cylindrical fin. So does that mean streamlined fin 0.5 model good fin efficiency in the trade-off relationships? Here is supplier heat dissipation performance in active environment. I constantly use fan that can produce air volume for cooling. If you use this fan for cooling, you can get more increasing flow velocity and flow rate. And operating environment is in the pink area like a high wind velocity area. So if you confirm thermal resistance RFA versus external wind velocity characteristics in this area, so cylindrical fin and streamlined fin 0.5 model shows same characteristics of thermal resistance RFA. But you confirm pressure loss versus external wind velocity in this area. The streamlined fin 0.25 model can reduce pressure loss significantly compared to cylindrical fin, about 48%. This means that if you use streamlined fin 0.5 model for cooling, you can get higher active point than cylindrical fin. So if you use in this active point, you can get high heat dissipation performance if you use streamlined fin 0.5 model. From this, high wing thickness like a streamlined fin 0.5 model shape are effectively obtain high heat dissipation performance in trade-off relationship. Here is summary. I talked about these four topics: research background and objectives, issues with major structures, method to solve the problem, last result. So this table shows that result more easily. So you know from this, optimal design of heat sinks in the trade-off relationship leads to the further heat dissipation performance improvement. Thank you for your attention.